what I was going to do here is this case study. I wanted to show the load profiles of 3 common devices that we see in our lives, not only at the industrial and commercial stage, but also in our homes. The CFL bulb, the LED bulb, and the incandescent bulb. CF bulbs, but a few years ago, they were the boom. You know, utilities were saying, okay, take out all the incandescent bulbs, put in CF bulbs, you'll save energy, you'll do all those things. But now they're kind of backtracking from that because now we're seeing some of the negatives of CF bulbs. Number one, they don't last as long as they were originally rated as, and there's a reason why that occurs, and I think I have a slide that shows that. Number two, and probably more importantly, when they fail, how do you get rid of them? The mercury content and things of that nature, so you just can't take them and throw them in the trash. I'm sure people still do that, but you're not supposed to do that. LEDs, they're the newcomer. The problem with LEDs are they cost probably on average 10 times more than a CF bulb. Incandescent bulb, probably next year you probably won't be able to get them. The government is really fighting hard to pull them off the shelf. So we're going to be, we're still going to be dealing with CF bulbs, but eventually once manufacturing costs decrease, then these bulbs will become cheaper, and that'll be the way to go. Now, I did some comparisons where I took a 60-watt CF bulb, 60-watt LED bulb, and 60-watt compact fluorescent bulb. And yes, these 2 devices here use about a quarter less of the power required for an incandescent bulb. So yes, there's your energy savings. However, these are nonlinear loads. They generate high third order harmonic. They're little harmonic generators. So the next time you look up and you see a CF bulb in your lamp or your light fixture, that's a little harmonic generator. Now again, the fortunate thing that we have for us is that the utility grid is low impedance, so it probably won't, you probably have to put 1,000 of them in your place, if you can, before the waveform is going to react, the voltage waveform is going to react to it. So that's kind of like our saving grace. But they both exhibit the same harmonic pattern. This generates no harmonic at all. It's linear, so it generates no harmonics at all. Failure of the CF bulbs has a lot to do with the startup. Because the stressing of turning them on and off, they get this startup, they get this inrush that stresses them and causes them to fail prematurely. If you had a CF bulb and you left it on, you're probably better off, believe it or not, you're probably better off leaving your CFL bulb on and not cycle it on and off. Then it will probably last close to the rated lifetime spec associated with it. And then of course there's you're only running at 1/4 of the usage of a incandescent bulb, so there is an energy savings there. But here's a startup of an incandescent bulb. We can tell that the load is linear because look at our current waveform. It's sinusoidal. That tells us it's a linear load. It's not going to distort the voltage. But here we see, just to kind of give you a point of reference, this is 7 amps. This is about 7 amps. The bulb will typically run at 1 amp once it's started up. So you can see that the inrush, when I initially turn on that bulb and flip the switch on, it's going to draw 7 times more of its normal running current. But it only occurs for like a half a cycle, and then it finally settles down. This is the CF bulb. Now with the CF bulb, the normal running current is less than 1 amp. So here you see the benefit of lower running current, lower energy usage, and so forth. But look at the startup associated with this. When this bulb comes on, it draws almost as high as 12 amps. Okay, the bulb is normally running at less than 1 amp, maybe 1/4 of an amp. But at initial startup, it's running high as 12 amps. It's that repetitive on and off that stresses the bulb out that causes the premature failure. You can even see that when I started up the bulb, I caused a voltage transient right at this point here. So the inrush was high enough to basically cause a little niche in the voltage waveform. And then obviously we can tell that it's non-linear because here's your normal running current. It has no sinusoidal characteristics at all. So we know that it's, this is the LED bulb. You can see that the LED bulb is not as severe as far as the startup. Here's before, here's the actual startup. You can see actually it kind of takes a while for it to start up. So it gradually comes up. But again, It's nonlinear. Look at the waveforms. You can see the waveforms are distorted. And it's all about having the right tool for the job.